Hello everyone, and thank you for that introduction. My name is Jeremy Meier, and I've been working alongside my colleague David No. We are both undergraduate computer science students currently attending Clemson University. We have been working under the supervision of Dr. Amy Apon and her lab for the past several years now, and have had some good experience with HPCC Systems and LexisNexis. We also have been working under the mentorship and supervision of Roger Dev. Our topic today is called an investigation into time series analysis. It has been a semester-long project looking all the way from the basic principles and components of time series forecasting to using modern machine learning models. The scripts we have written in Python can be easily implemented into a module for HPCC Systems, and our hope is to give you all knowledge for understanding, analyzing, and forecasting on time series data. But first, before I get into that, I have a quick question for you. How large are the time series data sets that you deal with? So the first question we're going to answer is, what is a time series? So a time series is a series of data points that are measured in regular or semi-regular intervals. The picture on the bottom left is actually part of a data set that you will see quite often throughout this presentation. I will give you a more detailed description of it later on. The important part is that it demonstrates for us what a time series data set looks like. It's a time series data set because, as I stated earlier, it is a set of data that was collected or measured at regular intervals, and in this example, daily. While a regression data set is something like the data set on the bottom right, there are multiple predictors. From this example, you can see income per month, loan type, and day. This is a big distinction between time series and other data sets, especially when it comes to analyzing and forecasting, and the different approaches that come along with those models. Continuing on with answering the question, what is a time series? A time series is a series of data points indexed in time order, and as mentioned before, a time series is a sequence taken at successive and equally spaced points in time. For example, recording the heights of the ocean tides, the number of sunspots, or even the daily closing value of the Dow. And there are 4 components which are usually associated with time series: cyclical variations corresponding to economic boom or bust, random variations that do not fall under foreseeable classification, and 2 other components, and these are the main focus of time series analysis. Generally, time series have some sort of seasonality and trend. A trend is the component of a time series that shows the overall movement in the series, ignoring the seasonality and any small random fluctuations. This can be seen in the chart below, where the data is on the top of the chart while the trend is in the middle. As you can see, the random and small fluctuations have been removed from the original data. And seasonality is the presence of variations that occur at specific regular intervals. This can be seen at the bottom of the chart, where the overall trend has been taken out, but the presence of small variations that are occurring at regular intervals are very obvious. Next, we thought it would be helpful to answer the question, why is stationarity important? But first, let's define the term. So a stationary time series is one whose statistical properties, such as mean, variance, and autocorrelation, are all constant over time. Thus, time series with trends or seasonality are not stationary. And in answering the slide's prompt, most statistical modeling methods assume or require the time series to be stationary in order to be effective. And that's why it's so important. As you can see in the chart below, the original data is shown in green. However, after what is called differencing, which I'll show in a coming slide, or making the data stationary, the variance and covariance have become constant. Intuitively, I think you can see why it's easier for models to use this kind of data, stationary data, for forecasting. To further explain why stationary data is important, I'll give you a high-level example. Let's say a time series is consistently increasing over time. Then a sample mean and variance will grow with the size of the sample. This will lead to a constant underestimation of the mean and variance in future periods, causing issues with many models used in time series analysis and forecasting. Now you might be asking yourself, well, how do I know if my time series is stationary? Well, first, you can always plot the time series and evaluate it just by looking at it. Next, you could review the summary statistics for your data for seasons or random partitions and check for obvious or significant differences. You can also use statistical tests to check if the expectations of stationarity are met or have been violated. The augmented Dickey-Fuller test allows a user a high degree of certainty that their data is stationary. However, it is a statistical approach and is not guaranteed to prove that your data is stationary. Now you might be wondering, well, how can I make my time series stationary? So there's a few things you could do. So it can usually be accomplished through the use of mathematical transformations, the first being differencing, as I mentioned earlier. The example that I show on this slide is called the lag difference, where one takes the difference between consecutive observations. The process of differencing can be repeated more than once, and usually it is done until all temporal dependence has been removed from the data set. The number of times that differencing is performed is called the differencing order. And a secondary approach is just called transformations, where you can take the log, the square root, or the cube root, etc. of your data set in order to make it stationary and meet those requirements that I stated earlier. And as you might expect, the series can be untransformed by reversing the mathematical transformations that you did previously. And now we will start looking into forecasting. But first, we want to answer just what is time series forecasting. So time series forecasting involves taking models fit on historical data and using them to predict future observations. Components such as trend and seasonality may also be the most effective way to make predictions about the future values, but not always. As shown previously, some models require that trend and seasonality be removed. Also, the future is completely unavailable and must only be estimated from what has already happened. And the performance is determined by how well a model forecasts the future. With this in mind, let's take a closer look at the data set we have worked with for this project in this semester. So our data set was called Stored Value Cards. It had around 16,000 total observations with around 115 accounts. It had two columns of data, making it a time series. It had a date, which would take it at daily intervals, and a value on each of those days. And these were opening balance values ranging from 0 to 10 million, which would represent the balance in the account. And the graph on the right shows about a month's worth of this time series data. And we will use this graph throughout the rest of this presentation when referring to our forecasting models and comparing them. So now we're going to start with a simple forecasting method called the naive or trivial solution. The simple or naive method is a forecasting technique where the value of the new data point is predicted to be equal to the previous data point. The result would be a flat line, since all new values take the previous values. From what we saw, the trivial solution is a really powerful tool for predicting one data value in advance, but the trivial solution begins to have trouble for multiple day forecasts. This can be seen in the graph below. The blue line is the actual data, and the red line is a naive solution. And we chose to show a particularly bad place in the data to use the naive forecast to demonstrate its weaknesses. And now we will look into some more advanced methods. These techniques are more advanced than the naive solution, but are still kind of simple. The simple average, the value that is predicted, the simple average predicts its value based on all previous values averaged together. And the moving average makes its prediction based on the average of the values in a given window, and not the entire set like the simple average, but rather just a window that was previous, and that can be set by the user. And as you can see, the window or lag can have a big effect on the forecasting accuracy of the method. So when doing forecasting on your own data sets, some fine-tuning will have to be applied, as you can see in those two charts below. And now we're going to dive into some more advanced forecasting methods, and I will let David take over from here. But first, I'll leave you with one more question. How familiar are you with ARIMA prior to this talk?
All right. Hi, everyone. Just to refresh, my name is David, and I've been working alongside Jeremy, Dr. Apon, and Roger Dev on this project. So moving on to more forecasting techniques, we have, first and foremost, the ARIMA model. What exactly is the ARIMA model? The ARIMA model is a popular technique for time series modeling. It describes the correlation between data points and takes into account the difference of the values and helps us better understand the data set or predict future trends. ARIMA works on two assumptions. The two assumptions are that the data is stationary and that the data provided as input must be a single variable series. ARIMA also takes in three major parameters. The three parameters are autoregression, integrated, and moving average, as shown on the slide. Autoregression is the path values used for forecasting the next value. Integrated is the order of differencing, or the number of times the differencing operation is performed on the data to make it stationary. And the moving average is the number of past forecast errors used to predict future values. So although ARIMA is a powerful model for forecasting time series, preparing the data and tuning the parameters end up being very, very time-consuming. Because ARIMA works on the assumption that the data is stationary, one would need to make the data stationary manually in order to find the parameters or the order of differencing. AutoARIMA eliminates these steps from ARIMA for us. As you can see in the chart, AutoARIMA takes out steps 3 to 6 from the ARIMA model steps. AutoARIMA basically does a parameter sweep and calculates the accuracy for each set of parameters. With these accuracy metrics, AutoARIMA takes the most accurate model and saves it. So here we have results from the ARIMA and AutoARIMA models' predictions on a dataset Jeremy described earlier. They both seem similar, but AutoARIMA hugs the second curve of the actual data closer and is almost identical to the first curve of the ARIMA's results, hence making AutoARIMA more accurate than the manually tuned ARIMA model. In conclusion, AutoARIMA saves time if you have not tuned the parameters for the ARIMA model yet, but it takes a lot more computational time. So moving on from ARIMA and AutoARIMA, there are two different modern techniques used for time series analysis that I would like to touch on. One being Facebook Profit and the other being a random forest model. For starters, Facebook Profit is an open source forecasting tool. Profit is a procedure for forecasting time series data based on an additive model where nonlinear trends are fit with yearly, weekly, and daily seasonality plus holiday effects. Profit shines for business forecast tasks or tasks with any of the following characteristics. 1, hourly, daily, or any type of seasonality. 2, important holidays. 3, a reasonable number of missing observations or large outliers. 4, historical trends. And 5, trends that are nonlinear, such as the trend that hits a natural limit or saturates. Moving on from Facebook Profit onto the last technique I'll be touching on today. Random forest is a supervised learning algorithm and can be used in many scenarios such as classification and regression. Also, a random forest is usually used in multivariate data comparatively to the typical time series analysis models that use univariate data sets. So here we have results from the AutoARIMA and random forest models' predictions on the same data set from before. As you can tell, the random forest model fits the curve more accurately than the AutoARIMA model does. In our case, the random forest fits better, but depending on the data set, the optimal technique or model can change. So I would like to end our portion of the presentation on another quick poll. So my question is, how likely is it that you will use time series analysis to solve your company's data problems? And with that, I would conclude our portion of the presentation. Thank you all for your time.
All right, fantastic, gentlemen. Thank you so much. So we're going to open the floor for questions. And while you guys review the questions and the questions from the audience list, let's go over the polls. First of all, let me jump back over to our first question, which was how large are the time series data sets that you deal with? Well, we had less than 1,000 records, 16%. From 1,000 to 100,000 records, nobody answered with an empty result. 100,000 to million records, we had 33%. More than 1 million records, we had 50%. So half of you out there work with large data sets, which is a pretty good thing. The second question in our poll, how familiar are you with ARIMA prior to this talk? I hope I said that right. And 62% have no familiarity of it. Only 12% have 12% were an expert, split 3 ways the other ways. So that was the second question, no familiarity with it at all. So it was a good topic to introduce all of us to. And let's take a look at the questions from the audience right now. So first question in the list, what approach to the data gave the overall best predictions?
Okay, so this is David once again, and the approach to the data that gave the best overall predictions for us was the random forest model.
Yeah,
all right.
we used about 1,000 decision trees for the random forest and got some very accurate results. But for those of you that might want to try and do that sort of model, 100 trees will also do it and save you a lot of computational time.
All right, very good. Next question, what was one of the biggest difficulties with making predictions on the data set? Good question.
This is Jeremy. So one of the biggest difficulties we had was just understanding the data, and there was some dates that were actually missing. So we were trying to understand how best we can account for that, and then also how do we kind of tune the data for the models. Like we were saying with making the data stationary, how could we make our data the best and most stationary for the ARIMA model or auto ARIMA? Those were a lot of the difficulties we ran into early on.
All right. Let's just take one more question. There's a few more lined up here, but I think we, our time here. What do you think? I think maybe just one more. Do you think this research has any possible useful business implications outside of the areas you discussed?
Yeah, I would say definitely. If you're better able to predict on maybe data that's relating to some sort of market or things like that, you could better invest in the future and things like that. And it also could supply or show anomalies in data. Perhaps if you know what the data should look like in the future and then you start seeing some weird looking results, you can perhaps know that the machine that's providing these results is giving you an error or an issue, and that way you can see anomalies better when you know what the actual data should look like when it's predicted.
All right, thanks. Just in closing then, what other collaborations or projects is Clemson University doing with HPCC Systems?
So I'll take that question. This is Dr. Amy Apon, and I've been the mentor for Jeremy and David this semester and actually over a period of several semesters. So we have worked on several projects with HPCC Systems. David and Jeremy and a couple of their colleagues worked on a project as an internship project on a text bundle where they were cleaning text to take out common words, and with a graduate student colleague also to identify what are called initialisms, different places where text, where characters should be collapsed into a single token. And I have two PhD students right now working directly with HPC Systems, one on optimizing k-means clustering, and actually that same graduate student is working on various ways to identify stop words in text for use in, say, topic modeling or text analysis. And these last two have been implemented in HPCC Systems. It's been an excellent platform for our larger text analysis research questions that we're asking.
All right, Amy, thank you so much for addressing that. That's wonderful. Good stuff. All right, so in closing, we have that last poll question. How likely is it that you will use time series analysis to solve your company's data problems? 33% said very likely, 11% said moderately likely, and 44% said likely. So that's a good chunk. That likely or very likely, that's over 80%. Only 11% said not likely. So good session, great introduction to time series analysis. We really appreciate it, guys. Thank you for participating. We really enjoyed it.